sessions. Okay, I hope the screen is visible to you guys. Okay, so one thing, first of all, thank you for joining. And as you know, this is the interactive session for this solid state physics NPTEL course, which is being taken by Professor Amal Kumar Das from IIT Kharagpur. And I am a PMRF research scholar, Mrinalini. I'm from School of Physics, University of Hyderabad. So these sessions, they'll be held every Saturday, 3 to 5 p.m. And what we'll be doing in these sessions is that every week, whatever lectures are released, based on that, I'll be doing some revision kind of things for few topics, and then related we'll be solving some useful problems so that it will guide you how to solve your weekly assignments, and also if you're going to take up the exam at the end of the course, so it will help you for that as well. So okay, so these lectures that we are having one-to-one right now, like live, we also will be recording these and they will be uploaded on the YouTube channel. The link will be there. I think you will be getting email where you will get, after these sessions, these PPTs will also you will find there, and as well as the link for the YouTube, so that you can later on as well access these lectures in case if you are not able to join the live session. Okay, with this, I think this information you guys have understood. So, okay, so let's start this first session. And also, I want to tell you, because right now my screen, the PPT is open, so I won't be able to see if anybody has any doubt and they are raising their hand the way we do in Google Meet. So, in that case, I would request you guys unmute and then let me know if you have any question. Okay. So, maybe you guys have already checked the website for this course, and there you may come across the recommended books for this course. I'm very sorry. This is first, second, third. There are 4 recommended books on the website: Elementary Solid State Physics and Introduction to Solid State Physics by Charles Kittle. These are usually very popular and basic kind of books. They are not things mentioned in detail, but they are correct. I mean, usually many local books, if we refer, there may be some misinformation, but in case if you want to go to a genuine thing, you can refer to these books. If you want, I have a soft copy of this Introduction to Solid State Physics by Charles Kittle. I can upload that in the Drive link where I'll be uploading this PPT as well. So I think I'll do that. And then this elements of XRD, when we'll be discussing this characteristic measurement, X-ray diffraction, that time I'll again tell, but for that topic, Elements of XRD by B.D. Kaliti is also a very popular book which many professors always suggest us for learning about the theory of XRD. Okay, so this is about the recommended books, and now let's start about this topic. So this week's lecture, I hope you guys have already watched and gone through those lectures. This week's lecture were very basic. We just started with atoms and lattice, which we'll do now again as a revision. And then, of course, I have some problems that we can solve together related to this week's topics only. Okay. So, solid state physics, when we talk about this subject or this course, so we know we are going to deal with, or we are going to study some that kind of things around us which has certain kind of state. We have very specific, okay, just let me switch on the pen. Yeah. So we are talking about solid state physics. That means we already have something in mind, that the kind of material, because states of matter I think we already learned in school, but still we'll have a quick revision of that as well. The states of matter that very commonly we see around us has a very commonly found solid state that we see around us. And this solid state physics course is, as the name suggests, is going to deal with these kind of materials around us. Now, talking about the building block of these materials, what these kind of materials, these solid states of matter are made up of. In fact, not only solid, but any kind of matter around us are made up of the building block that we know as atoms. Right? There are different types of atoms which combine through different kind of forces that again we'll discuss now little later. So there are different kind of atoms belonging to different elements, and they combine through different kind of forces to give molecules or compounds. So building block is atoms, which is made up of electrons, neutrons, protons. So the lecture as had started, and there was some discussion about different types of quantum numbers. So I think we can also do that first. So atoms, the basic what we know about, if we don't go to the if we don't go to quantum mechanics, because this also we know in quantum mechanics we don't talk about discreteness, we talk about waves, that matter is a wave and light is a photon, which is a packet of energy. So this happens in quantum mechanics. There we take electron also as waves, and we know that in quantum mechanics we are never certain about the position of electron because it's a very subatomic particle, right? But here we just keep the discussion, or very basic, like when until we are going to quantum mechanics, what we understand is how atoms look. We have a positive core, which we know is called proton, and then we have invisible, this is just for our understanding, that there is something like this circular orbit around the proton, which we call shells. And in these shells, we have electrons revolving around the proton. And because of this, we have angular momentum, orbital angular momentum. So this is what we discuss in classical mechanics. Here we don't talk about the electrons or the subatomic particles to be waves in nature. Here we are certain that the electron is revolving around this orbit around the proton. And here for this course, especially in the beginning, we'll stick to this understanding. And since we'll stick to this kind of picture of an atom, let's now understand in respect to this, what are the different quantum numbers and what they tell us. So we have 4 kind of quantum numbers. First is principal quantum number. So just now as we saw, I'll again draw, we have proton, and then these shells. Again, I'm repeating, this is just for our understanding. We just want to say that electron, if it's here, it cannot just randomly, there is particular path and there is corresponding particular energy. And this shell is n is equal to 1. This shell is n is equal to 2. If there is an electron, it will have energy corresponding to this n is equal to 2 principal quantum number. So we just want to say that this electron is revolving in this and it has this particular discrete energy. Another electron has this energy, so that's why we always depict it with this path. So principal quantum number, usually we denote it using small n, and the values are 1, 2, 3, and so on. And these values are this, the innermost shell, as we call it. So this innermost shell is n is equal to 1. It's also, we denote it with the English alphabets. Like for n is equal to 1, we call it K shell. N is equal to 2 is called L shell, right here. So n is equal to 1 represents K shell. Either we can call it n is equal to 1 or K shell. Both are same thing. N is equal to 2, L shell. N is equal to 3, M shell. N is equal to 4, N shell. And then further O, P, Q, and so on. So this is principal quantum number. Okay. The second type of quantum number is, either we call it azimuthal quantum number. I'm sure we already have studied these things in class 11th or 12th something. But since this course is basically for bachelor's students, so I think revising these things is not that a bad idea. I think it's quick revision is always good. And then this is usually represented by this small alphabet L, and azimuthal quantum number, or we also call it angular quantum number. Okay. Now this L has values 0, 1, 2, and so on up to n minus 1. What I mean n minus 1, that for any n shell, L will have value from 0 to n minus 1. That means for n is equal to 1, that is K shell, L or angular momentum quantum number will have value 0. And n minus 1 means 0, so only 0. Okay. N is equal to 2, which is our L shell, the second shell. N is equal to 2, that means L can have value 0, and n minus 1 means 2 minus 1, which is 1. And that's it, these two values. And for n is equal to 3, which is our M shell, we'll have L is equal to 0, 1, and 2. Always 1 less than the principal quantum number. And what this represents, L is equal to 0, we call it S subshell. L is equal to 0 again, that means N shell. Okay, so also these are called subshells. Like when I'm representing this energy level as shells, then in every shell, like in first shell, you see there is only one subshell, which we call L is equal to 0. That means here there is only this, which we call S subshell. Then there are two subshells for L shell, and this is S and P. Then we have L is equal to 0, 1, 2, which is three subshells denoted by 0, 1, 2. So sorry, this L is equal to 1 we call P, this, and L is equal to 2 we call D. So these are the subshells or angular quantum number. Yeah. So the next the next quantum number is the magnetic quantum number. Magnetic quantum number, which we represent by small m. Now in this also we have magnetic quantum number for this so we have something known as spin quantum number also. And this m, usually we use this for angular quantum numbers. What I want to say is, like for L is equal to 0, ML can have values from minus L going to 0 to plus L. since it's only 0, so ml can only take value 0. For L is equal to 1, ml can take values -1, 0, 1, plus 1. Now this, that means the P, I told you this is S subshell, this is P subshell. Now this P, how we can write? This P subshell can have 3 variations in itself. And later, or if you already remember, that we know as Px, Py, Pz. That is not necessary right now, but I mean it itself has 3 different states: -1, 0, plus 1. And for L is equal to 2, that is our B subshell. It will have 5. -2, -1, 0, plus 1, plus 2. These things, if there are in later in course, how we fill these subshells to find out the energy of atom or when it's in ion form. That time these knowledge of these quantum numbers becomes very, very important. So maybe we can revise this again later, but since it was part of this week's lecture and there may be questions in assignments as well, so that's why I am taking you guys through this as well. Okay, after this comes spin quantum number. And spin quantum number usually we represent like this, or even small s. And so we know electron has spin up or spin down, and that's why we represent it by +12 and -12. But just to be clear, that even though when we are talking about this motion of electron, and we say because the electron is revolving around in a circular orbit, that's why we get this, right? The angular momentum, we start from that, the value of moment comes from area that it's covering and the current, because it's a charge and it's moving, so we'll get current. So even though for orbital quantum number or for angular momentum, we can visualize that this is because of this motion we are getting angular momentum, but don't mistake or get confused. The spin quantum number is not so, or spin angular momentum, if you have studied in quantum mechanics, the spin is purely quantum mechanical phenomenon. What I want to say by this is, don't ever think that electron is actually spinning. Okay? Electron is not spinning. It's just the word that came, that is also, if in quantum mechanics you will study, because it was thought. This is how actually every time in science happens, that we have some hypothesis, we think this is how the phenomenon is happening, and then that time we just give it some name, later we get to know its actual reason or cause. So initially when something interesting was seen, it was thought that electron is actually spinning on its axis up and down, that's why the name spin angular momentum was given. But in reality, this is just a quantum mechanical phenomenon, and electron cannot spin on its axis. It will lead to violation of other laws and things. So it's not actually spinning, just to make this clear, because many times people have this misconception. So just to make that clear. But still we call it spin angular quantum number, and this helps in deciding various energies and other things when we discuss about some quantum mechanical phenomenon related to electrons or atoms. So okay, these were the little revision on this. Now I think we can move on to starting the topic of solid states. And again, I think it's better to have a quick revision of what kind of matters we have around and how they are different from each other. So the most 3 common that we easily see around us: first, solid state; right? Second, liquid state. Third, the gaseous state, vapor state or gaseous state. These are the very common states of matter we see always around us. And the other two, we can also say, the other two are not so common. A plasma state, we'll see what that is. And there is another also not seen naturally around, but it is a state of matter that has been uh, reached by scientists in lab. So we don't see it naturally around us, but just for knowledge or your information, this is also considered one of the states of matter. It's called DE condensate. It's on the name of two scientists, Bose, who was an Indian physicist, and Einstein, who I think you all guys already know, very famous scientist. So these two together had proposed something like this. That's why this particular state of matter has been named on these two scientists. So out of these five, these four we usually see around us, and the first three is very common we see around. Plasma state, okay, that we'll discuss where we see it and why it's, not common to see around. Okay, so moving forward, yeah. So solids, as we know, like here, for example, we have ice cube. We know if we hold, although ice maybe not good example, but still, okay, not ice, but something, anything actually. Say I have a stone in my hand, some shape of stone. I know it's rigid. That's how solids are defined, that they are not going to flow, they are rigid. How? Because that we just talked, what these matters are made up of. So the building block is these atoms. These atoms, because they are held tightly or closely together, that's what makes them into solid. Like for this ice, if it is frozen, the particles would be bound together. But if it gets sufficient temperature and it starts flowing, these atoms will start getting apart from each other. Then this won't remain ice. We start calling it, it's melting and becoming water. So all these states of matter, it only depends what kind of forces are acting between these particles and how rigidly they are held together. So again, for solids, the particles or the atoms that are making them, atoms or molecules, whatever. So when we use the term particle, we usually refer either atoms or molecules or sometimes ions as well. So these three things we just refer using this word particles whenever we are talking about physics or science. So in solids, particles are tightly or closed packed. The gaps between them are almost negligible and hence they are very rigid. That is tough to compress them. Solids have fixed shape and volume. This is what I am calling rigidity. And due to its rigid nature, particles in solid can only vibrate above their mean position and cannot move. Yeah, so what we mean is when we give heat to any solid material, the particles, the atoms, molecules will gain the energy, but they will only be able to vibrate at their position to and fro. They cannot leave completely until we give too much energy, and then they may change into completely something else. But usually with normal energy or temperature, they just can do this through to and fro motion at their mean position and cannot move. That's why they are solid. Like some metal bar. If I have some metal sheet, metal rod or something, if I'll melt it, if I give it some heat, if we touch it, we'll feel it's heating. That means it's taking up energy. But the atoms are not moving away. They are just doing the motion at their mean position. But if I give some 800 degrees centigrade or above that, then maybe it starts melting. then these particles will start moving. But then we cannot call it solid anymore, right? It will be molten something. Okay, so force of attraction between particles is adamant, is very strong. The rate of diffusion in solid is very low. What do we mean by rate of diffusion? If we keep, say, block A and block B, any kind of material, maybe let's say this is a steel block and this is a wooden block. Even if we keep them together for like 1 month, 2 months, 1 year, tied together, still they are not going to diffuse like this particle from here, this particle from here. Because again, what? The particles inside the wood are held together, particles inside the steel block are held together. So rate of diffusion is very, very slow. Even in some case, maybe there is sufficient heat in the atmosphere that they start, some kind of reaction starts happening, but it will be very low. So at normal temperature and pressure, rate of diffusion is very, very low. An example of solid, we all know, we see solids all around it, we have it in our hands, around us. So everything that is rigid, closely packed, we know they are solids. Okay, so now liquids, just now we discussed, if this ice melts, then it won't have any definite volume, it won't have definite shape. Sorry, volume would be same, but shape won't be definite. Then now the particles will have little weaker forces acting between them. So they will just like flow from wherever they'll get, in scientific term, wherever the potential energy will be less. But in layman's term, wherever we move it, it will be ready to go, unlike the solids. So what changes in liquids is particles are less tightly packed. And if you remember when it happens, because when we give it sufficient energy, when we give sufficient energy to this ice, that it melts. So where that energy is going? It's going in overcoming these bonds. Again, we'll soon be discussing about these bonds. So whatever this force is there between these particles, when we give sufficient energy and these bonds are able to break, then they don't care. No particle is pulling, attracting, or repelling each other. They are free on their own, and that's why they become this, like, without any definite shape. So we'll discuss about bonds soon. So they are less tightly packed because they are weaker bonds. Liquids take shape of container or wherever you throw them, they take just that shape. Are difficult to compress because again they are, of course, the bonds or bonds between them is not that strong, but still they are closely spaced enough that they cannot be compressed. Liquids have fixed volume but no fixed shape. That's what I corrected myself. That volume is fixed, of course, because the particle is not evaporating or going away anywhere. So volume is fixed, but shape is not fixed. So we should be careful with these terms as well. Rate of diffusion is higher than that of solids. This we can see if I have a glass of some juice and I have a glass of water. If I put the water here or juice here, doesn't matter. They will go and mix together, and then I'll have a more amount but diluted juice glass, right? So the rate of diffusion is much higher than solids. That there won't be any distinct layer until if some density difference is there. That is another thing. But if there is no problem in the density, then they will just mix with each other. So rate of diffusion is much higher than that of solids. Force of attraction between the particle is weaker than solids, of course, that's why they are flowy like this. An example is any liquid. This is very common, we all know: water, milk, blood, coffee, whatever, these things. Okay, now moving on to the third commonly found state of matter, which is gas. So in gas, if the same ice cube first we melted, that means we gave it some energy, so the particles were able to break the bond and able to move around freely. After that also, if I keep on giving it more and more energy, it will start evaporating and going up in the air, right? And then at the end, maybe nothing would be left in my pan which I was boiling initially, because all the particles, they gained enough energy. They even, whatever a little force was left in liquid state, they got sufficient energy to break that force also and leave completely out from the pan itself. Otherwise, you think, if you have a container, you have kept some ice cubes in it, even after 1 hour you will come, they will be inside only. Same with liquid, even if the ice will melt, it will remain here. But if you will come after several days, or if you start heating, basically, just the thing is that if we are giving it sufficient energy, which happens through evaporation or some other way, then these liquids will get enough energy. And say if I'm boiling, after few minutes maybe nothing is left in here, no water or ice that I started with. So where these materials go, it's not like they got destroyed. They, because I think this law we know that in nature matter can neither be created nor destroyed. Matter can neither be created, we cannot create them and we cannot destroy them. What we mean, it's not like we had ice in the beginning, now I have destroyed it and it became water. This is not what we mean by this. What we mean is it changes form. So the same particle, the same H2O molecules which were there here, the same H2O molecules are here, only the state has changed. Now the force between these molecules is weak, so overall the shape of the matter is changing, but the molecule is same. And in gaseous form also, because the intermolecular force is so weak now that it escaped out of this container, but it is there in the atmosphere, right? This is what we know as a rain cycle also, that whatever evaporation happens from the sea water, it goes to clouds, then rain, and come back to land and sea again. So the H2O molecules are same, it's just not here anymore. So matter can neither be created nor destroyed, it just changes its form. And the same goes with energy, that energy can also neither be created nor destroyed. It just changes its form from one thing to another, sometimes useful to not useful, and vice versa also. So okay, in gases the particles are far apart from each other. Forces of attraction is negligible, that's why they are so able to get far apart from each other, and they can move freely, as we see in air or any gas around us. Gases have neither fixed volume nor fixed shape. Shape we know, we just cannot talk about. In whatever container we put, like in case balloons, whenever we fill any kind of gas or air inside the balloon, depending on the shape of balloon, the air is the gaseous particles are accommodating itself. It's not, they don't care, or they cannot, how to say, control any shape of the container they are put in. So they don't have fixed volume also, nor fixed shape also. Why not fixed volume? Because the gaseous particles may escape out, like here. The gas H2O molecules cannot go out anywhere on its own when it's in the form of ice or when it's in the form of water. But if it started evaporating, then it will escape out of this container. So even the volume, you cannot be sure if after some time of boiling, the same amount is there or not. And of course, eventually everything will boil off, nothing will be left. So gases neither have fixed volume nor fixed shape. Gaseous state has highest compressibility. This again you know, in any kind of again say balloon kind of something which is very compressible, because the particles have lot of space within them. The particles are so far apart that there is lot of space when you're bringing them closer. So this, if you're compressing it, okay, they came very close. So the material, whatever it was compressible. But in solids, this doesn't happen. The particles are already very close. They cannot get distracted or again get even more close. That's not possible. So that's why they are not compressible as much as in this case. And the rate of diffusion, this we all know, is much higher than solids and liquids. If you have seen, we have some gas cylinders in labs. If you have seen in your scientific labs or somewhere, we keep it all completely packed. If is there any leakage or anything, it will escape out, and after some time nothing would be left, because their rate of diffusion is so high that they can easily go, and they don't need to be in this container for any reason. And if we have two gases kept together, they will diffuse very fast. Again, that was mixed together very fast. Kinetic energy of particles is higher. When I was heating this ice, which melted into liquid and then into evaporation, where all that energy went that I was supplying, as I said, energy can neither be created nor destroyed. So whatever energy I was giving, it was going, and the bonds between these particles were breaking. But after breaking, where it goes? So it changes into the kinetic energy of the particles. So in this case, it was just here, the particles were here, they didn't have sufficient energy to go anywhere else, right? In this also, they didn't have sufficient energy to escape out of this container. But in the case of gases, I keep on giving them energy, the thermal energy, and it gives them more and more kinetic energy, and they just go away from this container. So that's why they have high kinetic energy than in solids and liquids. Example is air, helium, nitrogen, oxygen, carbon dioxide, all these air, different kind of gases, cylinders that we see around us, or the LPG cylinder that we see around us. It's some certain kind of mixture of gases, but this is also kind of gas. And we know, if when we are using these kind of cooking stoves, we switch on the gas knob and we light the burner, and if we are not careful and the flame is off, then the gas will start spreading, right? We cannot even see. Their rate of diffusion is that high. Again, if you leave a glass of water, it won't go anywhere, but if you just leave the knob open and the flame is not lit, then the gas will go everywhere around. So we can easily see in around us these things that we are discussing, that they are less about their compressibility, about their rate of diffusion, about them being fixed volume or fixed shape. So these things are very common. Whenever, if I don't think anybody will have confusion, but if you have, just look around you and observe the things, and you will be able to see these things happening. Okay, so these are the three states of matter we discussed, which we very commonly see around us. But what about the two other states of matter that I mentioned? One is this called plasma, not very commonly seen around us. I don't think I have seen, okay, I have seen in labs, that is different thing, where we generate. So plasma is what? Plasma is consists of particles with extremely high kinetic energy. Just now we discussed in gas that particles of gas have kinetic energy higher than solids and liquids, because they gain energy from somewhere, and they are in this kind of with lot of kinetic energy. Plasma has even higher kinetic energy than gaseous state. That's why I said it's difficult to find commonly around us. And electricity used to ionize noble gas and make glowing signs, which is essentially plasma. So yeah, where you get to see, one thing is like in scientific labs, like I have seen in my lab, we have equipment, it's called magneton sputtering, if anybody knows. So what we do there is argon gas we use, it's a noble gas, and then we somehow make it highly energetic, and then we see very nice purple color filled in the chamber. So that happens at extremely, definitely not at normal temperature and pressure. We create very low pressure, and then high energy we provide for that to happen. Where we see this in nature, although not very commonly, but we see in nature, is stars. Because their surface, there are a lot of very exothermic reactions happening at the core of the stars, sun, which is also a star. There on its surface, this plasmas can be seen. because and the particles, whatever after the reactions are happening, the particles are which are having super high kinetic energy are around it, and those superheated forms of plasma is what we see around stars. So this is one place where we can see in nature, but again, yeah, not common, because the situation or the condition required to get plasma state of matter is very extreme. So that's why hard to see around us. But still, this is one of the state of matter apart from solid, liquid, gas. The fifth one, as I told, is based on two scientists, Bose-Einstein condensate. This state of matter is called. And I'm sorry, I don't have any picture because it's hard to get, even to visualize the picture of this thing, because it's not naturally found. We make it in very extreme condition. So we just, and it's not that relevant also, even if you don't understand, it's okay. But this is something that has been achieved by people. So I wanted to mention this to you also. So it was discovered in 1995 by these two people and made with the help of advanced technology only, not found around in nature. And yeah, we don't need to go in detail. It's just, this is something just for because you're science people, so you should have idea that there is something called this Bose-Einstein condensate, which also is called fifth state of matter. But again, not found in nature, only can be made with the help of advanced scientific technology. So what's special about it? It also shows superfluidity. It's superfluid, that makes it like it has no friction at all. It has its own usage and application that we can put it to. Okay, so these were the states of matter. Now, just now as I was discussing these states of matter, I was also telling you guys that there is bond that is breaking, there is attraction between these particles, or they are keeping together, there is some force between them. So now let's discuss something about these forces, and then we'll discuss interatomic distance also. Okay, first I think we should discuss about these bonding type of forces, or type of bondings also we call them. So in general, we have two types of bondings. We have two categories, primary and secondary bondings. So primary bonds are strong bonds formed by sharing or transfer of electrons between the atoms or molecules, while secondary bonds are comparatively weaker and based on temporary attractions. We'll see what we mean. So primary bond, which is also called chemical bonds, they are strongest, and the type of bonding under primary bonds is ionic bonding, covalent bonding, metallic bonding. Whereas secondary bonding, which is also called molecular bonding, they are generally weaker, and the primary bonds arise from intermolecular forces. The examples are van der Waals force, hydrogen bonding. These are two type of secondary bondings, and these three are type of primary bonding. Okay, now let's get deeper into understanding these type of bonding. So ionic bondings are formed when one atom donates electron to another, resulting in the formation of these positive negative charged ions. Like very famous example, NaCl, sodium in its valence shell has one electron. This Cl atom in its valence shell, and just to again recall that these atoms, they want, in fact everything in nature wants to have in equilibrium, or wants to have minimum energy. And that is what we see. If there is any hot body, we heat some cup of coffee or milk and we leave it, then after some time its temperature will go down and will come to in par with the room temperature. If we keep the same thing in a very cold place on earth, then it will attain the temperature which is near to its environment, because this is in every material, every system, every body on earth, in the universe, wants to be at the minimum energy, and that will be its equilibrium. So what happens is Na plus has one extra electron in its shell. If it give it away, then it will be attain noble gas configuration. Sodium, if we think sodium's electronic configuration, wait, is it's 7. Sodium has 7 electrons. So if we see how it's these electrons are put, so 1s2, 2s2, 2p2, I think, okay, 2p3. So if this will give this 1s2, 2s2, you can see they're already, these are the shells that I was saying. This 1s, then 2s. These are closed shells because they have electrons in pair. Whereas for this 2p3, okay, I'm sorry, I'm telling nitrogen, this is sodium, I'm very sorry. I think it's 14. It's 11, sorry. It's 11. So 1s2, 2s2, 2p6, and 3s1. I'm sorry. So these are all paired, but this 3s1, instead of 2, there is only 1. So it's not stable. If it will give this electron to something else, then it will attain the noble gas electronic configuration, where all the atoms will be paired, all the electrons will be paired, and the atom will be stable. So sodium wants to give off this to attain stability, and chlorine is an atom which has one, again, wait. What is the electronic configuration? Okay, I'm sorry, I don't remember, but I do know that it is one electron short of getting the, I don't have a periodic table with me, but okay. So it's one electron short. If it gets that one electron from somewhere, then it will attain a closed shell configuration. That is, all electrons will be paired and it will be a noble gas. Even so, what it wants is, it wants extra electron, this wants to give off extra electron. And when they are together, these two atoms, they tend to always form this ionic bonding. Because when this gives off its extra electron, Na changes to Na plus, because now it has given off its electron, so it has extra positive charge. Otherwise, its positive and negative charge were balanced, but now if it gives away its electron, it will have extra positive charge. So Na plus and Cl, which takes extra electron, will have extra negative charge, and this is a positive ion, this is a negative ion, and this gave its extra electron to this chlorine atom, made it chloride, became sodium ion itself, and by this sharing of electron, the kind of bonding between this kind of positive ion and negative ion is called ionic bonding. This is formed when one atom donates an electron to another, okay, resulting in the formation of positively and negatively charged ions. An example is this NaCl. But why will it give electron? I mean, why should it give? There should be any reason? We don't give off our valuable things to any random person, right? Until there is some benefit or there is some intention behind it. The same way, why do the atom needs to give its electron to, and to whom, and why? The reason is it wants to attain stability, and that it will get by getting minimum energy, and that happens when these electrons are paired. So that's why it's giving off. It's one atom. And then we get something known as this NaCl, which is our common salt. Another type of this bond is covalent bond. Here what happens, there is no giving and taking but sharing of electrons, and this happens usually in something like, if you remember, like carbon. So carbon has 12 electrons and its valence shell, other shells are closed, means they have all the pairing. In the last shell it has 4 electrons. If it will get 4 more, then it will attain stability, or if it will give all these 4 out, then it will attain stability, which is difficult. Giving of electron requires a lot of energy. We need to overcome attractive force and all. So instead of giving and completely away these 4, it starts sharing. Like one carbon atom will share with another carbon atom that also has 4 electrons in its valence shell. So if these 4, they will share each other, then both will in a way get 8 electrons in their shell, and this way they bond together and they get kind of stability. So this is also seen in O2 molecule, where they share electron to complete their outer shells. So this is one type of bond called covalent bond. Then we have metallic bonding. Now what happens in metallic bonding? This is found, as the name suggests, in metals where we have sea of electrons and they are free to move around, allowing the metal to conduct electricity and heat. So we know metals are good conductor of electricity as well as heat. Why so? Because in metals what we see that like in a metal, say if it's a sodium metal, then it is made up of Na plus throughout. And where is that electron going? It's like moving around in the whole, whatever, if it's a rod or block of sodium metal or a sheet of sodium metal. So the electron, because I told, it will be in a equilibrium or in a lesser energy configuration when it will give off electrons. So it's not difficult for it to give that off. Maybe with some thermal energy or just room temperature, it's able to give that off. And all those electrons, they are not bound to the atom. If they will be bound to the particular atom, then this is the case of insulators. That's why they don't conduct heat and electricity. But because they are loosely bound, means they are just going around in the whole volume of this material. That's why the metals are good conductor of electricity as well as heat, because the electrons are, as soon as we give some voltage, they will start conducting. The current. And if we start heating, they will start carrying the heat as well. So these electrons are very loosely bound, and because they are all over in the material, that's why we call it as sea of electrons, and they are very free to move around, allowing metals to conduct electricity and heat, and the positive metal ions are held together by attraction. So these positive ions are held together, they are not moving anywhere, but this valence electron is only what is moving around everywhere. So these are called metallic bonds. Now secondary bonds, which are called molecular bonds. So we have van der Waals forces, which are very weak attractive forces. They occur between molecules regardless of their polarity, arise from temporary dipoles. This is difficult to give example, but like if due to some reason some molecule is there and it just, that molecule means like say NaCl. When they combine, it becomes neutral. They are not any more Na plus and Cl minus. They are together. There is no extra charge, positive or negative. But if for some reason they get a little apart, that means we get negative here charge, like in this particular molecule, due to some reason the distance between these two ions increase. So at one side we get more of positive, another side we get more of negative, and the same thing happens with another NaCl molecule which is in the vicinity of this molecule. Then this will start attracting, this is positive, this is negative. This will be very weak. It's kind of very momentarily, because NaCl is not always in this Na plus Cl minus form, where it will be a little positive on one side, a little negative on another side. Usually it's just neutral together. But if due to some reason this kind of thing happens, then it will make the another NaCl molecule also to become, this is called dipole, because it has two poles, right, positive and negative. So it will induce another molecule also to become little a dipole, because it will attract the negative part. And this is kind of force between like these two NaCl molecule, and it usually very weak, and it's because they arise from these momentary dipoles that occur when electron distribution around atoms fluctuate. Okay. Now another is hydrogen bond. Now this is little stronger than van der Waals force, but still they come in the category of secondary bonds. So a strong type of secondary bond that occurs when hydrogen is covalently bonded. Covalently means sharing, not giving, not transferring, not taking, only sharing. Bonding to highly electronegative atom like oxygen or nitrogen. Electronegative means they just need one electron to become neutral. So they are looking to get that one electron from wherever possible. They are very ready to take that electron from somewhere. So they keep on looking for any kind of atom which can easily give them this extra electron that they need. That's why they are very reactive, and they are called electronegative, or electron affinity also this phenomenon is called. So hydrogen has only one electron, and it can easily give it to oxygen or nitrogen to form this hydrogen bond. And this creates a significant dipole, allowing hydrogen to attract other electronegative atoms. Examples of hydrogen bonds: H2O, hydrogen, two hydrogen connecting with oxygen, right? Or NH3 or acetone, ethanol, these things. Okay, so this was all about type of bonding in matter. Basic category is primary, also called chemical bonds. These are strong kind of bonds. Another is secondary bonds, also called molecular bonds. They are relatively weaker kind of bonds. Okay, so now let's see. So these we just discussed, these are various types of matters, then there are various types of bondings in those matters. Now what, like, because we are studying solid state physics, so what is the, we already know of course that in solids we said that they are very closely packed, they are not free to move because there is some force acting between them which is keeping them together. But then what is the distance at which they are there, and they are not going far away from that, they are not even going closer than that particular limit, and they are stable at that distance. They are stable at that distance. Otherwise, if they are not stable at that particular distance, I mean, these are atoms. Just to tell you, these are atoms, and they are happily sitting at those distance between them. They don't want, if we have to remove them, then we have to give energy. If we want to bring them closer in solids, that is also not much possible. So why they chose this much distance, which we also call interatomic distance, because it's the distance between the two atoms. So between the two atoms, that's why we call it interatomic distance. So why they choose to be at that particular value of distance, this we'll get to know. Just to tell you rough values, because also you must have seen it was mentioned in the lecture that for solids, usually, again of course it differs in different kind of solids depending on different kind of elements, but usually in solids the interatomic distance is 2 to 4 angstrom. Angstrom, 1 angstrom means 10 to the power minus 10 meters. Okay, so when we are discussing about atoms and these subatomic particles or atomic particles, we get to, instead of always saying 10 to the power minus 10 meters, we start talking in angstroms or nanometers. Okay, so these are the units that we use. So why they, yeah, we were discussing why they are comfortable at this distance, why they are stable at this particular value of distance. So what happens is, oh, I can tell, yeah, the other two values also, like for liquids, Usually for liquids the interatomic distance is 5 to 10 angstrom roughly. It's not anything like certain. It's just about, I'm telling you the range. For gases, as we know, the atoms are very far away, so the interatomic distance has to be more than this, and it is actually about 30 angstrom in the range, about 30 angstrom, about 5 to 10 angstrom for liquid, about 2 to 4 angstrom for solids. Okay, so again coming back to the question, why they choose to be in that particular distance. So what happens is, for let's take one atom, it has positive core, of course, and then electrons revolving around the shell. Okay, this is my atom 1, and then I have same material, so number of electrons and charge, everything will be same, just another, now like the same whatever element this is the same element, another atom. I'm taking atom 1, atom 2. Even if it's another atom, the understanding and everything will be same. That's not a problem, but still, just to keep it simple. Same material, different atom. I have positive core, electron is there. Now we know positive charge, positive charge, when they come around each other, they repel. This we see everywhere, be it magnets or anywhere when our hands or something get electrostatic charge on it, depending on if they get close to positive charge, they will repel. If they'll get to opposite charge, which is negative charge, then they will attract, right? Or negative charge is coming in vicinity of negative charge, then that will also repel. So we say like repels and like attracts. This is for the case of our charges. Now here in atom 1, I have a positive core and electron which is negative, that is around here. Now for another atom also same, I have positive area or positive region, positive core at the center and electron revolving around. Now if I'll start bringing these two atoms closer, it's just for imagination because it's very inhumanly possible to, I'll be holding two atoms which are so small in size and everything and bringing them together. That doesn't make sense, but just for understanding that if somehow I have these two atoms, I'm bringing them close together, then this negative charge of electron and this negative charge of second electron, after at particular some distance, when they come close each other, if they're far apart, then there's nothing going to happen because the range is not that much. But if they are at some particular distance range, then this electron will start repelling this electron because same charge, negative. This positive core will start repelling this positive core. So there should be repulsion. Then these atoms should not come close at all. But we see in solids we have the atoms together. Then where does this attraction is coming from? Now this negative is repelling the negative. This positive core is repelling the another positive core. But the electron of this atom 1 can attract the positive core of the second atom. It's repelling same charge, but it will always attract the opposite charge. Because again, why? Because that leads to lesser energy. The same with this positive core and this electron will have attraction between them. So there are two forces acting, actually four. Electron repulsion, positive core, they are repelling. And then there is electron of atom 1 attracting positron, positive core, nuclei also we call, of another atom. Like this is for atom 1, this is for atom 2, this is also for atom 1, atom 2. Okay. Now the positive core of first atom is attracting the electron of second atom. So both situations are happening. Repulsion situations also are there, and attractive forces situation is also there. So ultimately, what the atom will do? There are chances what I mean. There are situations leading to its repulsion also. There are situations leading to attracting these two together also. Then ultimately, what happens with the atom? So that could be seen here. Um, don't get overwhelmed. So just to simplify, what we have here is this is y-axis. This I'm showing energy of bonds. Bonds are formed when these two atoms will come close together sufficiently enough. Then we can call bond. And then on x-axis, I have the distance between these two atoms. The same these two atoms we are discussing, and this is the distance between these two atoms. So it's been seen, we don't need to go why exactly this is happening, but it's okay for us to just understand that this is how things happen with bonding. That when the particles are at, we know the this is 0, that means as we go towards this side the distance is increasing, right? So when the distance between these two atoms is, say, this much large, the attractive force dominates. Okay, so the overall graph looks something like this. And what this tells us is that at higher distance between these two atoms, there is attractive force which is dominating, which is given by this 1 over 4 pi epsilon naught minus e square by r. And then when they get very close, again depends on the kind of atoms we are talking about, so I cannot tell you exact value, but when it gets very close, then the repulsive force starts dominating, okay, which is given by 1 over r to the power n. So here repulsive force is there, here attractive force is there, then a balance between them is when the energy is minimum. I told you every system wants to be in equilibrium, that is at the minimum energy. So these two atoms will get equilibrium or the minimum energy situation when the distance between them is this value, which we can call r naught. Okay, and this is called the equilibrium distance, and that is why we have solids with atoms not too far, not too close, but at equilibrium distance until you give some energy and they start vibrating and they start drifting apart. If you don't give it energy, it is at peaceful state, equilibrium state, minimum energy, then this is the equilibrium distance they will attain, depending on a lot of constants that are there. So the in total, the total energy will be contribution of attractive energy, attractive force and repulsive force, and the total expression looks like this. So the total force between the atoms, the expression can be given by A over r to the power m minus b to the r to the power n. R is the distance, A, B, M, N are different constants and they depend on the kind of material or the kind of atom we are dealing with. This is repulsive force part, this is attractive force part, and wherever there is a balance between these two, the atoms attain that as equilibrium distance. So this is why they come to that particular distance, because everything in nature has a reason, it's not random. And for here, this is the reason that it wants to attain minimum energy, that is equilibrium, and at this particular distance the repulsive force and attractive force, it balances each other, and that's why without any compression, without any repulsion, they just peacefully sit together. If we increase due to giving some energy, it will not be in equilibrium anymore, and then things will change. But this is the reason that I explained. They want to be in this particular equilibrium interatomic distance. Okay. So, and Yeah, I think this was also discussed last time, that the expression of force we got from here. Now to find out the energy, we know energy. Okay, so energy will be, because force is this derivative of potential energy, or E also we can denote energy. So energy will be, when we integrate the force expression, we will get the value of this energy expression. And after doing this, you'll see the expression that we get is minus, using this expression, A over Rm and B over Rn. When we integrate this, we'll get A m plus 1 Rn minus 1 plus n plus 1. Simple integration this is. So this is the expression, and since I told these are just some constants, so I can change it and write it into simpler form also. That is, if I just take this a multiplied by m plus 1, say I denote it with small a, and this m minus 1 I denote it with another expression, say m prime, let's say, and then this will be small b n prime. What this b is, this whole thing, this n prime is this n minus 1. Either you can just keep it till here or keep it till here, just for the simplifying the expression. So this is the value of energy, and now we want to find out where the energy will be minimum. Means the du by dr, it will be minimum when the derivative will be 0, and when we'll do this is E or U. Usually for energy we very commonly use the alphabet U. That's why I'm writing U. But here, if you're comfortable with using E alphabet, that is also okay. It just means the same. So when we take derivative of this and equate it to 0, we'll be and put, then we'll get what is that equilibrium distance. So that comes out to be, this is very easy derivative, and this thing you can do. So this is that equilibrium distance which the atom will take. And then B, A, all these parameters again depends on the atom. So for particular atom, if we know these B, A, N, M values, we can find out the equilibrium distance R for that particular atom. So this was a discussion with why atoms tend to be at particular distance, equilibrium distance in the matters. Now I think, yeah, we'll move our discussion further and go specifically into types of solids. Now types of solids, we have broadly categorized crystalline and amorphous solids. Okay. So crystalline solids, as you can see, all these blue balls actually are representing atoms here. These are all atoms. These are also atoms. But we very clearly see, even though both of these, let's say these are inside a beaker, so both are same atoms, I mean in this particular case, but still there is something very different. We can distinguish this pattern from this. Why? Because here the atoms are arranged in a very regular way. There is some kind of arrangement here, but here there is no arrangement. They are just lying around, or just like the way they have just been put, it's very random here. Where here there is some regular kind of arrangement or pattern. So when in solids there is this kind of regular pattern, then it makes the atoms, if are regularly placed or put together, they make a solid material which we call crystalline. And when they don't have this pattern or arrangement, then we call them amorphous material. Now, even in crystalline, we have variety like single crystal and polycrystal. Amorphous example is glass. So if you zoom in or magnify a piece of glass sufficient enough that you can see its atom, difficult, atoms are very small in size, less than angstrom. So about angstrom. So it's difficult to see, but still if you magnify, you will see the atoms or whatever the particles made up of which are making up the glass. They are not arranged in a regular pattern, and they are that leads to their different characteristic, that they lead to they are brittle and other things, whereas for crystalline materials they are more tough or some other kind of characteristics which come into picture when they show crystalline behavior. And single crystal polycrystal, what I mean is, if you have something like this, that I have this chunk or this piece of material and the atom is arranged throughout, then there is only one kind of arrangement, so it's called single crystal. But if instead of this arrangement being throughout, the arrangement or this pattern is in small portion, what I mean by that is, say like at in one portion of whatever material I have, the atoms are arranged like this, and after some time they are arranged like this. Then after some time their direction changes. I don't know, I mean different things. Something is changing. So there is pattern. I have this block of material. There is some pattern, but it's restricted to small area. So then it's called polycrystal. There is some crystalline behavior, but it's very not throughout the material. Then we call it short range actually. This single crystal have long range ordering, or this regular patterning, we give it scientific term long range order. Single crystals have long range order from the beginning till the end. Polycrystals have short range order. They have some ordering, but it is only up to smaller distance, up to short range. So this is polycrystal. Okay, this will be in some other direction, maybe chunk. So in glass, no ordering at all. No ordering at all. No pattern, no regularity. Okay. So single crystal, polycrystal, glass, or just broadly we can categorize to crystalline and amorphous. So because our discussion soon is going to be very much based on this. Okay, so now in this also, so if you have seen the lecture, there was a concept introduced when we are talking about solids: lattice, basis, crystal structure. What do we mean by these scientific terms? These are very important for understanding, not the definition. I don't think it's important that you know word to word definition of these basic terms, but it's very important to have clear understanding what we mean when we say lattice, when we say basis, when we say crystal or crystal structure, so that we don't get confused. When we say lattice, first let me just read out. This is how we define lattice. Lattice is a mathematical concept, not actually, but just something. Mathematically means we can visualize, but it's not actually like that. I'll tell you why. It represents purely geometric periodic arrangement of points. This is lattice. This I'm showing you here, lattice. Okay, we'll get to there. So it's a periodic arrangement of points. This is one point, second, third, fourth, then again. Now you can see there is some, if only one point is there, we cannot say it's regular or periodic or not, because this is just single. We don't know where this pattern is going or not. But if we see more points arranged together, we can see, yes, there is some pattern we can easily see. This is that this point is at this particular distance, there is some regularity, there is some periodicity. So when points which are just mathematical concept, dimensionless structure, when we arrange them in space, right now I just have 2D space, so I have arranged it in 2D manner, but they have been arranged in periodic way. This abstract thing, okay, this is not actually, we don't see points around us. This is very abstract, but we need this to get to the crystals which we have around us, right? Like NaCl crystals or some kind of other iron unit cell or something. So those things we have, but these things is not actually there, but we need it for to get to understand how we get crystals. So this is just abstract concept, but it is based on periodic or regular arrangement of points in space. Now to every point, if I put an atom now atom is very much real. These points are not, they are abstract. Atoms are very much real. So if I put my atom at this position, then this position, all these points on top of these points, if I place my atom, now these points were all at fixed distance from each other. They had a particular periodic arrangement. So when I put my atoms at those positions, now even my atoms are following that arrangement, are following that periodicity, right? So this is why we need basis, so that we can tell how our atoms are arranged. Now this basis doesn't, okay, so this is what we call basis. Basis is the specific arrangement of atoms. Basis is not atoms, okay? We don't call atoms or basis. We are saying specific arrangement of atoms or molecules associated with each lattice point. This point that we were talking about, we call, in when we study about crystals and solids, we call it lattice point. It's just the name given to it. So when we put all at these lattice points our atoms or molecules, we call that basis. This basis can be single atom, as I showed you here, or it can be group of atom or molecule, or even sometimes complex structure. The example is like here. This is one lattice arrangement. The points are, instead of being just below each other, they are at some particular angle, but we can very clearly see that they have some pattern. They all are at this maybe 60-degree angle to each other. So pattern is still there. This is just lattice point arrangement. Now if I put this purple atom, purple ball, whatever you want to call, at these positions like this, then we will get something like this. And atoms are real, so this arrangement is very much real, and this gives us our crystal structure. So lattice is a mathematical concept. It's arrangement of abstract points. Basis is what is real, and when we arrange this basis or atoms at these positions, then we get our crystal structure, which we were talking about, that if it's arranged for long distance, we call it long range or short range, that we just saw here, right? So you can imagine there's nothing actual point here. We cannot, there's nothing to be seen, but we can imagine there's a point here. And we are just putting our basis or our atom at these positions and getting this crystalline arrangement. So this is what we mean when we say lattice plus basis gives us crystal structure. Now this here, our basis was only one atom. It was only single atom arrangement at every lattice point. What if we have something like this? This is like one atom joined with another atom. This is one molecule. And now we keep this molecule at every lattice point. That's why I said it's not like atom is equal to basis. No. This whole together, when it's corresponding to every lattice point, it gives us the crystal. So we are talking about the arrangement actually. So this basis, when we keep at this lattice, second lattice, third lattice point, fourth lattice point, we see something like this. Again, we see there is arrangement, there is periodicity. Okay, so this is what we mean by lattice, which is a mathematical concept, but periodic arrangement of these mathematical points. And basis is the specific arrangement of atoms associated with each lattice point. It can be single or group of atoms. And then when the basis is put at every lattice point, we get our crystal, which is formed by combining the lattice and the basis. And this is what gives material its physical and chemical properties. Okay. So this was about lattice and basis. So please keep in mind these terms. These are very, very important for further discussing our topics. And I think it's, yeah, maybe we have less time also remaining. So I think we should move quickly to the problem solving. And then these are the things which were like the discussion was initiated this week, that we have 7 type of crystal system and 14 type of Bravais lattices. Maybe we can discuss this anyway. We'll be discussing this next week interactive session. So I think now I'll just move quickly to this. And if we have time left, then maybe we can still discuss it again. But yeah, so till now we covered the basics of solid state physics and solids and type of bondings, type of states of matter. And now let's move on to doing these not assignment problems, sorry. I mean, these are some questions that I brought from somewhere, so that solving these will help you in solving your assignment problem. Okay. So the first question is, transfer of electrons takes place in which of these bondings? So we have already discussed the bondings, and we know transfer of electrons takes place in ionic bonding, right? Like for example, Na very happily wants to give out its extra electron and become a positive ion. Chlorine atom wants one extra electron so that it can become stable, and so electron is going from here to here, and because of that they bond together, and the bonding is called ionic bonding. So this transfer of electron happens in ionic bonding. A is the correct answer. Yeah, so because I was forgetting earlier, so just to give it a closure, when I was discussing that sodium has 11 electrons, so its electronic configuration is 1s2, 2s2, 2p6, 3s1. Okay, now this 3s1 can accommodate 2 electrons, but it has only 1. If it will give away this one, then it will get all paired electrons, and thus it will be stable. Whereas the chlorine, whereas this chlorine has a number of electrons 17, electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so 3p5. Now if it will get this p, right, I told there are 3 subshells in it, 1, 2, 3, 4, 5, and only 5. If it get one more, then it will attain stable in electronic configuration. Stable electronic configuration. Okay, and it will become what? After stable electronic configuration, it will become argon gas. And this, after losing this extra one, it will become neon, which are noble gas. They don't react that much because they are stable. So this is the electronic configuration, and that's why sodium wants to easily give out this extra electron, not extra, but wants to happily give out this electron to become stable, and chlorine happily wants to accept one more to attain a stable noble gas configuration. That's why the transfer of electron happens so easily between these 2 atoms, and they form NaCl bond, which is a very strong bond. Ionic bonding is very strong kind of bonding. Okay, moving on to next question. Among the following bonds, which one is the weakest? We have if you recollect, we discussed primary bond. Broadly, we saw the category is primary bond and secondary bond. Now, under primary bond, there were few types. Under secondary bond, there were few types. And we had seen primary bond is stronger than secondary bonds. So, among the following bonds, which one is the weakest? Covalent bond, that is type of primary bond. Ionic bond also is type of primary bond. Metallic bond also is type of primary bond. This happens by sharing of electron. This happens by sharing of transferring of electron. Metallic bond is also when electron just revolve around the positive cores, but they are not leaving still. Van der Waals bond, as I said, it happens when suddenly, due to some reason, NaCl, instead of staying neutral, they get at some distance and becomes something like a dipole. Then this portion has positive charge, this portion has negative charge, and it's maybe momentarily happening, and that's why when it attracts or makes another NaCl molecule to convert it to dipole, because of this positive charge inducing negative charge, and this is very weak and it's type of secondary bond. So the weakest among these four is van der Waals bond because it's the secondary bond happening in this kind of situation. Okay, next question is van der Waals bond is formed due to electron and core interaction. We know electron and ion core interaction happens in metallic bond, right? There's positive core everywhere and then electron moving around them. That happens in metallic bond, which is strong. Dipole-dipole interaction, as I just now told, Na plus Cl minus suddenly, due to some reason, when they, initially they were like this. Due to some reason, the positive part comes to one side, negative part comes to another side. Then for a moment they have this separation of charge. Yes, that is the term. For a moment, due to some reason, they have separation of charge. They are not completely neutral anymore. Then that is called dipole, right? And this we see attracts another dipole. So this dipole-dipole interaction is what leading to van der Waals bond. Coulomb interaction, sharing of electron is not the answer. Dipole-dipole interaction is the correct answer. So option B is correct. Fourth question. What type of bonding exists between water molecules? Water molecule, if you recollect, water molecule means H2O, very popularly called. We have oxygen and then hydrogen bonding like this. The bonding between this is hydrogen bonding. It has one electron. It has two electrons short. It has 6 electrons in valence shell. If it will get 2 more, it will be stable. So there is sharing between the hydrogen and oxygen, and they form very stable bonding, which is called hydrogen bonding. Okay. Usually it's bonding seen between hydrogen when it bonds with oxygen or nitrogen. So that is also one way to identify. Okay. And next question. Which of the following bond is directional? So actually, covalent bond is called directional bond because, so the meaning of covalent bond is being directional is that atoms bonded covalently prefer specific orientation in space. I told we have like methane, say. Okay. So here it's not hydrogen bond just because there is hydrogen. No. Hydrogen, therefore, four hydrogen, and carbon has 4 valence electron. Hydrogen has its own 1 valence electron. They will share together and they will form this CH4. Now this is directional because prefer specific orientation in space relative to one another. As a result, molecules, atoms are bonded covalently, have definite shapes. Unlike ionic bonds, where there is no electron sharing, a number of anions surrounding a cation is limited by charges of ions, their sizes, and lattice packing. Okay, so the reason for this directionality is that covalent bonds are formed by sharing electrons between atoms and overlapping of atomic orbitals. Usually, you always see NH3 denote like this. It's very directional in that case, the sharing, because otherwise if they come closer there will be repulsion between them. So that's why they maintain this kind of shape. That's why covalent bonds are called directional bonds. A is the correct option. Which of the following has hydrogen bonding? So although I told you it's very easy to see if you have a hydrogen atom around, but not always the case, right? Sometimes maybe hydrogen atom is just doing a covalent bonding. So be careful. Here we have CH4, but we know carbon has 4 valence electrons. So it cannot give, it cannot take. Most probably it's just making covalent bonding, which is true. Now CSCl, this is again example of ionic bonding. NaCl, we have been discussing it for quite long now. This is case of ionic bonding. HF is the case of hydrogen bonding, not the charge I want to show. I mean the bonding between hydrogen and fluoride ion is they're covalently bonded, but that comes depending on the strength there is. It comes under hydrogen bonding. Maybe this kind of chemistry questions may little more to chemistry side may not be there in part of your assignment this time. It's still just I brought from a lot of sources, so it's good to have some idea. Now moving on to some mathematical problems. So first question is the Coulomb interaction, the interaction between the atoms, the forces, it's known as Coulomb forces, Coulomb interaction. So this question is Coulomb interaction energy between two adjacent ions in a solid. Okay, so we have two adjacent ions in a solid and the interaction energy between them. As I told, we can use either U, E or any alphabet if you want. Just meaning should be clear. So here the expression for energy is being denoted by capital U. So we will stick to this. The expression of the interaction is given to be like this, and then electrostatic unit. It's not that important, but just some unit. The energy should have some unit, right? Then find out the bond length of the system at equilibrium separation. As I told, when two particles, two atoms, two charges come close together or anything, there is some kind of attractive force, some kind of repulsive force. So here we have two adjacent ions. We don't know if they are positive ions or negative ions. They could be negative, they could be positive, they could be positive, negative. We don't know. We're just being told they are two adjacent ions and the interaction energy between them is given by this expression. Then at what distance they will be happily sitting around each other, neither facing repulsion nor facing attractive force. They will be just in equilibrium. So the way to find out their distance is that first we take derivative of this energy, okay, du by dr respect to r, which is the interatomic distance or interionic distance here. First we take derivative, so we'll get, I hope you guys remember how derivation is done. Let me just tell. Derivative of, just to recall, if you remember d by dx, or we used to do, or if you want me to stick with r, then derivative of 1 by r with respect to r will be minus 1 by r square, right? Just or let's see, derivative of 1 over r to the power n will be minus 1 over r to the power n plus 1, and usually derivative of r to the power n will be n times r to the power n minus 1. So this, just recall that these were the derivative rules. So when we take derivation of this expression, we'll get minus is already there, then again we'll get 1 minus, and this will be a by r square. Then here we have b, then there will be n as well. There will be minus n and r n plus 1. Okay, and this will be a over r square minus n times b over r n plus 1. Okay, now we have taken derivative. Now this derivative will be equal to 0 for equilibrium. At equilibrium, let me slide. I need some more space here. So at equilibrium, this derivative will be equal to 0 at r is equal to r naught. The distance will be, I mean the atoms or ions will be at equilibrium when they will be at this equilibrium distance that we denote by r naught, and the derivative will be 0. So equating this thing to 0, what we get is a over r square. I'm taking this expression to another side, so I'll get n times b over r. Okay, so after putting r is equal to r naught, it will be n plus 1. Then if I take here, it will be r naught n plus 1 divided by r naught square is equal to nb divided by a. Now this, what it will become, so the r naught n plus 1 minus 2, right? This r naught square, when it will come in numerator, it will be minus 2 is equal to nb over a. It implies that r naught n plus 1 minus 2 means n minus 1. N minus 1 is equal to nb over a. So value of r naught, which is the equilibrium distance value that we want to find out, if I will take exponent 1 over n minus 1, right, then it will become 1 and this side will become, I think these, the way of doing this maths, you guys already know. In case if you have doubt, you can ask me, I'll explain it even in smaller steps. Otherwise, if you can understand, then that's also good. If we are just taking the power both side, this. So the equilibrium distance finally will have this expression. If you know B, A, N, all these, then we can find out the exact value, magnitude. But if we don't know these constants, then we can just say that B is the correct answer. This is the equilibrium distance at which these two ions will sit without facing any attractive or repulsive force. Okay, the similar way, I think we have few more questions. More specific this time they are. So here the question is, KCl crystal, energy of interaction between adjacent ion. Now we know A and B constant here because it's for particular KCl molecule. So interaction between adjacent ion, the interaction energy can be given by this expression. And we have to determine the equilibrium energy at equilibrium ion separation. So we have to find out the energy. This is the energy expression, but the distance is known. If we find out the R naught, equilibrium ion separation or equilibrium distance between the ions, then we can substitute the value of that R here and we can find out the equilibrium energy. So first our job is to find out this equilibrium distance or equilibrium ion separation. That we know how is to be done is, first we have to take the derivative of this energy expression, equate it to 0 after putting R is equal to R naught. Same thing we will do here. For this, when I'll take the derivative, you can do, I'll try to do faster steps because our time is going to end soon. So yeah. So equilibrium energy, when I take derivative, I'll get expression 1.436 divided by R square, and when I'll put R naught, it will be R naught square, okay, minus 9 times 9 will come from here, right? 9 times 5.86 times 10 to the power minus 6 divided by r to the power 10 r naught. I took derivative, then wherever it was r, I put r naught there, and then I equated it to 0. This is the way to find out r naught. Now when I simplify this, I will take this expression to another side. So it will be 1.436 divided by r naught square. I'm taking it to right side, so it will become positive, right? 9 times 5.86 times 10 to the power minus 6 divided by r naught to the power 10. Now again what I will do, I will bring this denominator to this side, it will become numerator, r naught to the power 10 divided by r naught square. Now this I can calculate actually, let's just calculate. Please, I have my calculator with me for this. So 9 times 5.86, 52.74, 2.74 times 10 to the power minus 6 divided by 1.436. This will become this r naught to the power 10 and r naught to the power 2. When this will come to numerator, this will become r naught 10 minus 2. And this side of the expression, when I calculate, sorry, 52.74 divided by 1.436, it will be 36.727 10 to the power minus 6. This will be r naught 8. R naught to the power 8 is this. So when I want to find out r naught, that means I have to take 1/8 power on both sides. Again, let me just take more slide here. So this r naught 8, r naught will become what I got, 36.727. 36.727 times 10 to the power minus 6, this whole to the power 1 by 8, right? So the equilibrium distance will be this, and when we calculate this, we'll find out the expression to be 0.279. And because the unit here, you see the unit was energy unit, even the answers are an energy unit, so that means the distance is this units. We don't know angstrom or what exactly, but some units. And then we have found out the equilibrium distance. Now we need to find out the equilibrium energy at equilibrium distance. For that, in this energy expression, we'll keep the value of equilibrium distance, which is 0.279. When we substitute, we'll get Q is equal to minus 1.436 divided by 0.279 plus 5.86 times 10 to the power minus 6 divided by 0.279 to the power 9. Okay. When you calculate this, we'll get minus 4.57 energy units. So this is the correct answer. So ultimately the force is attractive between these two ions. Okay, that also tells us one is positive, one is negative, or different things also, but this is the correct answer here. So this is the procedure to go about when the question is asked about the equilibrium energy or equilibrium ion separation. We have one more question. Let's do it. Calculate the cohesive energy of copper given the bond energy between two copper atoms is this. So there are two copper atoms and they together form a bond, and the energy between them, the bond energy is 56.4 kilojoule per mole. Consider effective number of bonds in FCC is 6. Effective number of bond in FCC is 6 and cohesive energy to be 6 per bond. Okay. So here we have copper which is FCC. This also, there's simple cubic, body center cubic, or FCC. If you're clear, then I think you already know this also. If not, then maybe we'll be discussing it again next time, where we will discuss crystal system, or what we mean when we say simple cubic, body center cubic, or face center cubic. But if you have seen the video, or the lecture video of this week, then I think you already know that when we have 3D unit cell, right? And then at the corners we have atoms, and then at the face of this box or this unit cell also we have atom, and that kind of structure is called face centered cubic structure. And in this situation, maybe we can revise this thing in next time also. But when we have FCC unit cell, then the nearest neighbors are 12 in number. Okay, this is one face, and if you see, these 12 atoms are all nearest to it. So here, when we are talking about copper atoms, then we know if it is in FCC unit cell structure, then we have 12 coppers which are at same distance with each other. So here we are talking about 12 copper atoms. Why? Because it is in FCC structure. Okay, now we have been so as we see that between two copper, one bond is there. That means if we have 12 copper atoms, then we will have 6 bonds between them. Okay, and the formula to get this number of bonds is the effective number of bonds between atoms is given by number of neighboring atoms divided by 2. So here, because it's FCC system, so there are 12 neighborhood atoms, and then divided by 2 means 6 bonds we have between these 12 atoms. Okay, so we understood number of bonds. Now energy for one bond is 56.4 kilojoule per mole. That means we have 6 bonds here. That means total energy for one bond is 56.4 kilojoule per mole. That means energy for 6 bonds will be 56.4 times 6 kilojoule per mole, and we can calculate, and this will be 338.4 kilojoule per mole. Okay, now what we have to find out, consider effective number of bond is 6, and cohesive energy we have to find out to be energy per 6 bonds. Again, I think I can solve here as well. Okay, so finally the cohesive energy will be, because it said the cohesive energy is per 6 bond. Total energy is this, that means total energy for 6 bonds is 338.4 kilojoule per mole, which is our answer. This is the correct answer here. Okay, one last question. Yes, potential energy of a system of 2 atoms is given by this expression. A stable molecule is formed with release of -8 electron volt of energy when interatomic distance is 2.8 angstrom. Calculate the values of A and B. So in earlier cases, we were given this energy expression and we had to find out the interatomic distance. Now we are given the interatomic distance and we have to find out the value of these constants. Okay, so the way of doing this is same. Again, the potential energy expression that is given for this particular molecule, we'll take derivative of this. After taking derivative, we'll put R is equal to R naught and equate to 0. So why we do this, if you, in case you missed, so when we take derivative of energy, we get force, and this force is 0 at equilibrium distance. The distance r0, which we are calling equilibrium between atom 1 and atom 2, when these atoms are at equilibrium distance, there is no force acting between them. That is, no repulsion, no attraction. Then they achieve this stable energy situation. That's why, and this force is derivative of potential energy. So the force becomes 0 at equilibrium distance. That's why we are taking derivative and then putting r is equal to r0, and this makes the expression equivalent to 0. Okay. So when we take derivative, then we get here the expression becomes minus 2a divided by r cube plus 10b divided by r to the power 11. And when we equate it to 0 and putting r is equal to r0, at equilibrium distance we have force is equal to 0, so this thing we can equate to 0, and then we can, if I take this to right side, then it will be 2a r0 cube 10b r0 11, and then either you can, if you are able to understand, then that means yeah, this is the shortcut I can do. So this will be r0 to the power 8 is equal to 10b over a. This is one expression that I got. Yeah. From, and so this is one equation, and from this equation okay, so this is, I found this value of r0, and in terms of, okay, because r0 value is already given, so when I substitute it here, it becomes 2.8 to the power 8 divided by, no, let's do this, a I am bringing this side, then it becomes 10 times b over r0 to the power 8. r0 is 2.8 angstrom.
Ma'am, there is 2A.
Sorry?
Ma'am, it was 2A actually.
2a. Oh,
Yeah,
yeah, yeah,
ma'am.
okay, thank you. Yeah, thank you, sorry. I just need one more slide. Okay, so this will be, there was 2a, so we can cancel out like this also, so it will be 5b by a, then a will be 5b and divided by 2.8, and this is just angstrom to the power 8. Okay, when we solve this, not solve, we'll just keep it like this, a is equal to 5b, and for time being we can just keep it, or let me see, 2.8 to the power 8, that's a big value. So this angstrom, 2.8 times 10 angstrom, 1 angstrom, I told you 1 angstrom is 10 to the power minus 10 meters. So put this and take its power. So we'll get, maybe we need to calculate right now. Okay. Now another, this is one expression between A and B we have found out. Just a minute. This, okay, let me just calculate this thing. 2.8 to the power 8 is 3778. So this 5b divided by this will be 3778.019, and this will become 10 to the power minus 80. And when I'll divide 5 by this number, I'll get 1.32 times 10 to the power, and then this because there will be 1.32 times 10 to the power minus 3 times b divided by 10 to the power minus 80. So it will be 1.32 times 10 to the power 80 minus 3 will be 77 and times b. So this is the relationship between a and b, 1.32 times 10 to the power 77b. But still we need to find out the value of a and b. So we need one more equation, and that we can get from here. Let me take another. So we already have energy expression, which is minus a over r square plus b over r to the power 10. So if here I'll put, we need to find out the value of a and b, and we already have the value of energy. Putting this here, I'll also put the value of a that I have obtained in terms of b. So it will be minus 1.32 times 10 to the power 77, 10 to the power 77, and this are not at equilibrium, or the value is minus 8 electron volt when these are at equilibrium distance. So putting that value here that we obtained, that is given actually 2.8 angstrom. So 10 to the power minus 10 and square of it plus b, it is still unknown. This is in terms of b, this is still unknown, and then 2.8 times 10 to the power minus 10 to the power 10. When we'll solve this, we'll get the value will be like this. So this is, it's getting complicated. Yes. Means 8 electron volt. One electron volt actually is 1.6 times 10 to the power minus 19 joule. So the energy is, because the distance is in meters and all, so the equivalent unit for energy is joule. So this we use here. So it will become minus 8 times 1.6 times 10 to the power minus 19 this side, and when we'll solve all this, we'll get, it will be some expression in terms of b. From here there will be some magnitude, right? We'll get the value of b by taking this side in the division. We'll get some value of b, and then when we'll put this value of b in this equation, we'll get the value of a also. We are running out of time, but if we solve this will 10 to the power minus 20, 10 to the power minus 10, so we will get 10 to the power 8 expression here when we multiply. So I think you guys can try solving this. We'll get some expression here. We have to divide this left hand side by that. We have to take care of this energy conversion, and we will get expression for b from this equation. When you put it here, we'll get the value of a, and the answer will be, so the answer, I'm just letting you know, the final answer is, this is the correct answer. So this is the value of a, this is the value of b when you solve this peacefully. So I think these are the all 10 problems that we had, and since time is also up, I think if there is any query right now, you guys can ask, or later also I think there is one discussion forum where you can post your questions, so we get notified, we can maybe answer there, or of course in next interactive session, if you guys have any doubt, you can ask about today's any topic or any of the problems that we discussed. So if there is nothing, then maybe we can end today's session? Okay, if there is no question, then I'll stop